So this is an example of how to do the problems from 10.1. So in 10.1, you remember we're looking at two populations that are independent, and we want to compare their means. So here we start off and we see the problem is about a branch of a bank that's located in a commercial district, and they want to improve their process for serving customers around the lunchtime period. And first they decide to study the waiting time, because they have to know if they're improving, right? They have to know what it was originally. And so the waiting time is defined as the number of minutes that elapse from the time the customer enters the line until they're being served by a teller. And they go ahead and they collect data on 15 individuals. It's a random sample. And also there's a second branch that is interested in improving their waiting time too, and they also collect data. Okay, and then the part A says assuming the population variances from both banks are equal. So these are banks that are not the same bank. Okay, so we're just looking at, say, one branch of one bank, one branch of another bank. So if we assume the population variances from both banks are the same, is there evidence of a difference in the mean waiting time between the two branches? Okay, let's go ahead and get the data first. So we're going to do bank 1 and bank 2. And let's see, we'll go to my stat lab. I want to go to course home, actually. So what we want to do first is we want to actually download the data, right? Okay. So we'll go to StatCrunch. And now we go to Chapter 10, and we want the data from Bank 1 and Bank 2. So we're going to have to download both of them. Okay, so I'm just going to select all. I'm going to say Control-X for copy. And here I'm going to enter Bank 1 and just paste the data. And there's already a header, so I might undo that and just paste it and then put Bank 1 here. And now I'm going to do the same thing for Bank 2. So go back here. Now I'm going to download the data for Bank 2. So select all, Control X, and we'll go ahead and paste that. And these waiting times are in minutes. We always want to be kind of cognizant of what our units are here. I'm going to center each of these. Okay. There we go. Okay, so we're all set. I'm going to insert a column here too, because there's a few things that I'm going to want to compute. Okay, so this is my data I'm going to be working with. And now what do I want to compute? Well, if we look at the formula for the test statistic, okay, this is the formula for the test statistic. On the quiz, I will give you this formula. Notice that I'm going to need the average from both of those samples, and I'm going to need the sample size, and I'm going to need the pooled standard deviation, which is going to be really just some arithmetic function of the individual standard deviations from each of those samples. So what I need first is I need X bar from each sample, and I need S, the standard deviation. And I'm also going to get N, although, you know, I kind of know N. If I'm not sure and I want to be really careful, I can just, you know, make some list here just on some sort of numbered list, and I can see it's 15, although I've already been told that. So okay, so now we're ready. So let's go ahead and compute the average. Try to fit everything on one page here if I can. Okay, so I'm just going to say equal average, and I'm going to get X bar for the first. The nice thing about Excel is if I just drag this over, it'll automatically do it for the other column. And I'm going to say sample standard deviation. Okay, I'm going to go ahead and highlight all that. And then I'm just going to drag this over. Whoops. Okay. And N, even though I could, type it in, I'll just do this. And when you drag it, Excel will copy that also. Okay. Notice I could have made life, it shifted this cell over. I don't want that. Never mind. Let's do this. Okay. Notice that I could have done all these formulas at one time and then just drag the whole thing over. In other words, let me show you if you want to kind of save time. I'd have to anchor this actually. It's probably a little more work than it's really worth, right? But notice that if I highlighted this whole thing and dragged it over, it'll automatically do all these calculations for me, so save you a little bit of time. Okay, so now I have the main summary statistics I need to do my computations. But before we do that, let's get into the hypothesis tests first. And I could compute a few more things. So I think I'm going to compute a few more things because I want to make the computation of the test statistic a little bit easier. Okay, so here I'm going to compute S squared. I'm just going to square the sample standard deviation. I don't have to do this. I could do this in the part where I'm computing the test statistic, but I'm just going to do it here because it's easier. Okay. And I'm going to compute SP squared. Notice I'm going to be using this n-1 a lot, so I'm going to go ahead and just compute this. It's actually going to come in handy because when I'm computing degrees of freedom and whatnot. Okay. So now I'm going to focus on this formula. Notice this formula becomes very easy. The numerator is just this times this plus this times this divided by this plus this. So now I'm going to compute what we call the pooled variance. It's the pooled standard deviation squared. So if we use the formula, it's going to be equal to this times this, n-1 times the sample standard deviation squared for the first sample, plus n2 minus 1, right, times this squared. And I want to divide the whole thing by n1 minus 1 plus n2 minus 2. So I have to put a parentheses around the numerator. Okay, and then I'm just going to say, oops, this plus this. Okay, and the last thing I'm going to compute is the sample, pooled sample standard deviation. This is what we call the variance. The variance is the square of the standard deviation. So the standard deviation is just the square root of the variance. Okay. And there's a reason why I want to compute that. The reason why I want to compute this is I'm going to compare it to these two values. This value should always be between the sample standard deviations, because this is kind of like an estimate of the average of these two. Okay, it's kind of like a weighted average if you look at it. And this looks okay. This is between these two. I'm going to round everything off just a little bit to make life easier to 2 decimal places, just so it looks nicer. It's easier to read. If I have to copy a number, I'm a lot less likely to make an error if I don't have as many. Whoops, what am I doing? I want to do format, right? If I don't have as many decimal places. And there we go. Okay. So now we're ready to do our actual hypothesis test. So for part A, we're going to do a hypothesis test. So first we have to state the hypotheses. And so our null hypothesis and our alternative are just going to come from reading the problem. So it says, assuming the population variances for both banks are equal, is there evidence of a difference in the mean waiting times? So I'm trying to prove that the mean waiting times are different. So this is going to be mu1 minus mu2 is not equal to 0. And this is going to be that it is equal to 0. Okay, so these are my two hypotheses. Okay, second thing I'm going to do is I'm going to calculate the test statistic. And so okay, so if I look at this, I see that it's going to be x1 bar minus x2 bar. This is 0 because this is what's going to be on the right-hand side for hypothesis test. So we know that in general, this difference is going to be d. This is basically what we would call d. Okay, so mu1 minus mu2 is equal to 0. This would be this quantity here. Okay, so it's going to be 0. And then I'm just going to divide by the pooled variance divided by n1 plus the pooled variance divided by n2 and take the square root of the whole thing. Okay, so I'm going to say this is my test statistic, which is going to be d. It's going to be equal to, and I'm going to have to contain the numerator in parentheses anyhow, so I'm going to do this. So it's going to be x1 bar minus x2 bar divided by square root of, and I'm going to compute this, I'll tell you what, I'm going to back off 1 minute. I'm going to compute the standard deviation of x bar separately. So the standard deviation of x bar, I'm sorry, of x1 bar minus x2 bar. That's going to be this denominator. I'm going to compute this off to the side. So this is going to be equal to, let's see if I can fit everything on one page. It's going to be the square root of the variance divided by n1 plus the variance divided by n2. So it's going to be the square root of the quantity, this divided by, make sure you pick n1, plus the same quantity divided by n2. I'm going to close off the square root. Okay. So now the test statistic actually becomes very easy to compute. Because now the test statistic, if you remember, the test statistic is just going to be equal to, in our case, x1 bar minus x2 bar divided by standard deviation of x1 bar minus x2 bar. Okay, so let's go ahead and compute what that's going to be. So that's going to be equal to, and this is x1 bar minus x2 bar, and I'm going to divide it by the standard deviation of x1 bar minus x2 bar. Okay. And so this is my test statistic, and you can see it's very large. Okay, so I know already I'm probably going to reject. Okay, even if it's a t-statistic, when it has a value of greater than 4, that's considered very large. Okay, now we want to compute the p-value. Okay, so two things that we want to bear in mind. The first thing is that that t here comes from a t distribution with n1 plus n2 minus 2 degrees of freedom. And the other thing we want to keep in mind is that we're doing a two-tailed test. Okay, so what we're going to do here is we're going to find the percentile that this value is in for a t-distribution that has 28 degrees of freedom. So we're going to use t dot dist, but I have to multiply my final answer by 2 because I'm doing a two-tailed test. It's going to be t dot dist, and this is my value here. I'm going to do n1 plus n2 minus 2, and it's going to be true. Notice I didn't have to do 1 minus because the test statistic was negative, so the percentile is going to give me the right value there. And just as we predicted, the p-value is very low. And let me actually move this over to the other cell here. I'm going to put this over here. Okay. So this is my p-value. And it's usually not a bad idea to round this off again so you can see this a little better. I'm going to round this off to 3 decimal. I'll do 4 decimal places. Okay. Okay, now the rest is very easy actually, because I'm going to go ahead, I'm going to use my decision rule, which will always be the same no matter what sort of hypothesis test that we're doing here. So this says p less than alpha implies reject H0. So we want to ask the question, is p less than alpha? Well, p is equal to 0.003. Our alpha here is, 0.0003. Our alpha is 0.05 in the problem, right? So this is less than 0.05, which is equal to alpha. So just as we expect, we're going to reject H0. Okay. So now all we have to do is we just have to state our conclusion. So we would say at a significance level, of 0.05, we conclude that the average waiting times between the two branches are different. And you can state this in different ways. There's not, one way that you have to state it. But that's pretty much all there is for the hypothesis test part. Okay, in B, it asks, determine the p-value and interpret its meaning. So the p-value here is 0.0003. So for B, so our p-value is equal to 0.0003. And so what this means is the probability of finding a test statistic as far from 0 or further than the test statistic in this problem is about 0.0003, or equivalently, we could say 0.03%. In other words, it's very unlikely to find a test statistic this extreme. Okay. Notice that we said as far from 0 because with a two-tailed test, it could be on either side. If we had had a test statistic of positive 4.13, we'd have the same p-value, right? So that's our answer for part B. Okay, part C is saying, in addition to equal variances, what other assumptions are necessary? Well, there are a few other assumptions we need, right? We need to know that the data is normally distributed. So there's two more assumptions we need. The first assumption is that the variances are equal. So number one is that the variances of the samples are equal. Or you could say standard deviation, it's the same thing. Assumption number two is that the data comes from a normal distribution. That's a rather strong condition, actually. If the sample size was sufficiently large, you wouldn't have to worry about it, but this sample size is actually small. Okay. And the third is that we have a random sample. Okay. And we have these three things we can go ahead and we can use this t-test. Okay, and the last part is asking us about a confidence interval. It wants us to estimate the 95% confidence interval for the difference in the waiting times. Okay, so for part D, we want to find the 95% confidence interval. So we need a few things here, right? We need the confidence. That's 0.95. We need alpha, which is 1 minus the confidence. Okay. And now we remember what the confidence interval is. So we know that the confidence interval is equal to x1 bar minus x2 bar, plus or minus the margin of error. And the margin of error, we recall, is equal to the critical value times the standard deviation of x1 bar minus x2 bar. Okay. Notice we've already found all of these things except the critical value. I computed the standard deviation of x1 bar minus x2 bar up when we did the hypothesis test, so that part's known. And we know x1 bar minus x2 bar, that came from our sample. So all we need is the critical value. So the critical value is equal to the t-score for a t-distribution. Well, I actually want the t-score for, we're just going to say the alpha over 2 percentile of a t-distribution having n1 plus n2 minus 2 degrees of freedom. All right, so we're going to go ahead and do that, and that's just going to be t-inv, right? We're going from a percentile to a data value. So it's going to be alpha divided by 2. And my degrees of freedom, I could put 28, but I'm just going to click on the cells. This plus this. Notice that the formula bar is up here, so I can still see what I'm doing. Okay, and that's going to be a negative number. I'm going to correct that when I compute the margin of error, because now the margin of error is just going to be equal to, I'm going to take the absolute value, okay, of this times the standard deviation of x1 bar minus x2 bar, which I computed way up here. Okay. And so there's my margin of error. And now we're ready to go. We have everything we need. So 95% confidence interval therefore mu1 minus mu2 is equal to, I have to compute the lower and the upper endpoints first, so I'm going to go ahead, I'm going to insert a few cells here just to make life easy. So first I'm going to do the, I'll do the lower endpoint first, which is just going to be equal to x1 bar minus x2 bar minus the margin of error. And so I have that information. I go up here and I take x1 bar minus x2 bar minus, and my margin of error is right here. Okay. I'm going to compute the upper endpoint, and I'm just going to cut and paste because this is the easiest way to do this, really. Change the negative to a positive. This becomes the upper endpoint. And of course I'm going to change this too. So I'll cut and paste this. And then just change this to a positive. Okay, so there's my upper and lowers. So now I'm going to go ahead and say that the confidence interval is, minus 4.23 to minus 1.43. And I'm done. Notice that we said this before. We said that the 95% confidence interval is the same as a hypothesis test conducted at alpha equal to 5%. So remember what this means. It means that when I reject the null hypothesis at 5%, D cannot be in the confidence interval at 95%. And D was 0. Okay, this difference, this number D, when I reject the null hypothesis, cannot be in the confidence interval. And you see that it's not. Recall, that's how I caught myself in the last class, and I realized that I had made an error computing things in, because you have no sense for what these numbers should be. So knowing these rules of thumb are in fact very helpful. I'm just going to format things to make everything look nice. Okay, and that's all there is for that problem.